This is slide number 66 and I am your presenter Asloob Mudassar. Joint transform correlator. Next we describe joint transform correlator, abbreviated as JTC, as an alternative to the Waterloo filter based correlator. In JTC, desired impulse response and the signal to be filtered are presented at the front focal plane of first Fourier transforming lens L2. The figure is given on the next page, which I am going to explain soon, which are illuminated, that is the signals are illuminated simultaneously by an identical plane wave. The Fourier transform of both O as a function of zeta and eta and O2 as a function of zeta and eta appear at the rear focal plane of lens L2, where they can be recorded using special light modulator or can be recorded on a photographic plate or on photo glass. The amplitude transmittance of the combined input when they do not overlap is given by TA, that is the amplitude transmittance of the object as a function of zeta and eta, is equal to O for the object O, which is located at the coordinate zeta comma eta minus y naught, plus the object O2, which is located at the position zeta comma eta plus y naught. So let me show you the figure. So this is actually the figure. Let me read the caption. Two signal transparencies, O as a function of zeta and eta and O2 as a function of zeta and eta, that is both are located at the same plane, that is at the zeta and eta plane, and but symmetrically placed in the joint transform correlator. So you have object O. You see that I have shown object O over here at the object plane. The object plane is located at the zeta and eta coordinates, and there is an object O2. So O and O2 are located at the object plane, which you can see in the form of clear apertures. But these are not the clear apertures, but these are actually the object O and O2. And the rest of the region is opaque, which means that the objects do not exist in that region. And you know that this object is illuminated by the beam output from the lens L1, which is a plane wave, because the point source is located at the front focal plane of the lens L1. So the lens L1 receives spherically diverging wavefront from the point source, and the lens L1 will convert them into plane waves. So both O and O2 will be illuminated by the same plane wave, and the lens L2 will generate the Fourier transform of both O and O2 at the Fourier plane. So at the Fourier plane, if you place a spatial light modulator, or if you place photographic film, or if you place photo glass, then you can record the absolute Fourier transform, absolute value of the Fourier transform over here. So that recording can be once the photo glass is illuminated, then you know that after the illumination or the exposure on the photo glass, you need to develop the photo glass and then dry it. So then that dry portion, then that dry film will be referred to as the joint transform correlator filter. And that filter can also be placed back over here for further processing. Okay, the input signals are located at the object plane at a distance y0 symmetrically about the zeta axis. So you can see that both these objects are symmetrically located about the zeta axis at a distance y0 above and a distance y0 below. So O is located at a distance y0 above the zeta axis, and O2 is located, that is the center of O2 is located at a distance y0 below the zeta axis. Intensity recorded on the photographic plate or recorded on the photo glass placed at the Fourier plane is given by the following equation. So the intensity at the Fourier transform plane. So we are actually giving you the expression for the intensity at the Fourier transform plane, that is I as a function of a Fourier frequencies fx, fy. So that is equal to the absolute square of the Fourier transform of the amplitude transmittance of the objects at the coordinate at the plane zeta and eta. So you see that that will be equal to the absolute square of the amplitude transmittance of these two objects, which are going to be transformed by the lens L2. So you can see the Fourier transform operator within the absolute square bracket operating on the operating on the amplitude transmittance of the object. In the second step, I have placed the TA, that is the two objects from equation number 28. So the two objects are placed within the curly bracket and the Fourier transform operator is outside that one, but exists within the absolute square bracket. So this in the third step, the Fourier transform operator will operate on O and will also operate on O2. So when it will operate on O, the Fourier transform is given by 1 over iota lambda f multiplied by capital O as a function of fx, fy, and e to the power minus iota 2 pi fy into y naught. This is the Fourier transform of the object O. And the Fourier transform of the object O2 can be similarly given by 1 over iota lambda f multiplied by O2, which is the spectrum of O2 as a function as a Fourier frequency, as a function of a Fourier frequency fx, fy multiplied by e to the power plus iota 2 pi fy into y naught. So you see that capital O is the Fourier transform of small o object, and capital O2 is the spectrum or the Fourier transform of the object O2. So here you see that this will give you the intensity that we have to record for the JTC, that is for the joint transform correlator. The further explanation, the further processing of this signal, that is the last step, is given over here. So you see that we have in the first step shown in the blue, you have the two signals and also multiplied by the two signals with its complex conjugate, because we have the absolute square of this quantity, which means that the quantity within this absolute term will be multiplied by its complex conjugate when we remove the absolute square term. So we have this O written in blue, and then you know that in the red we have a multiplication of these two terms within the parenthesis bracket. So the total there are 4 terms we have shown over here. So in the red we have actually applied the conjugate symbol to the individual terms on the second parenthesis. So you can see that on the second parenthesis you can see that O is replaced by O conjugate and capital O2 is replaced by capital O2 conjugate. So in the third step we are going to in the third step, which is shown in blue, we have multiplied all these terms over here. So you can see that there are terms within the curly brackets in the last step in blue, which is the absolute square of capital O as a function of fx, fy, then absolute value of O multiplied by capital O multiplied by O2 star, and then e to the power minus 4 pi fy y naught, plus the third term is O2 as a function of fx, fy multiplied by capital O star as a function of fx, y multiplied by e to the power plus iota 4 pi fy into y naught, and plus then the absolute square of the O2 as a function of fx, fy. So you see that equation number 29 is the simplest form of the equation that we started with this one. So actually this is the intensity that will be recorded on the photographic plate or on the photoglass. So you see that once we expose the photographic material or the photoglass with this intensity given on the left hand side as I of fx, y, fy, and their full expression is given at the end of equation number 29, then you know that after exposure of the photographic plate or the photoglass is removed from the setup, and then it goes under the process of developing and fixing and then drying process. And then when it is dried, then it becomes a joint transform filter. The amplitude transmittance, which we refer to as a T, subscripted as JTC, standing for a joint transform correlator. This absolute transmittance as a function of fx, y of the photographic filter is related to I as a function of fxy as given in equation number 30. So you see that in the equation number 30, look at on the left hand side, which we have T as a function of JTC. What is the JTC? Joint transform correlator. So actually this is the transmittance of the amplitude. This is the transmittance of the joint transform correlator filter, which is proportional to the intensity given above. That is the last expression of equation number 29. So the transmittance of our filter which we have developed and which we have fixed and which we have derived, and then that becomes the joint transform correlator filter, and this is the transmittance of that one, which is proportional to the intensity that we have shown over here in equation number 29. So this is proportional, not equal. The JTC mask with amplitude transmittance JTC as a function of fx, fy is the Fourier transformed by the length L4 of the setup shown below. So you see that we place the filter over here in the setup as we have shown JTC filter. This is a filter. This is actually the same plane as the Fourier plane. So in the Fourier plane we exposed we exposed our photographic plate, and then once it becomes a JTC filter, then we have placed the filter over here at the same Fourier transform plane, and then you know that illuminated by the plane wave. Okay, this JTC, then you know that is inverse Fourier transformed by L4. L4 is another Fourier transform lens that takes the inverse Fourier transform of the JTC filter and then give you the image at the image plane. So you can see the separation between the lens L4 and the filter plane and the image plane equal to distance f. So let me read the caption. Coherent system used to obtain output at the image plane due to the JTC filter located at the front focal plane of the lens L4. So the amplitude distribution UIMG, that is the amplitude image, you can say UIMG is the amplitude image at the coordinate at the plane u comma v at the image plane, because the image at the image plane we have the coordinate u and v. At the image plane is found by taking the Fourier transform of T JTC and is given below. So you need that we need to this length L4 will take the inverse Fourier transform which we have written over here, and the image will formed at the image plane. So we have amplitude image u with the subscript of IMG as a function of u and v is proportional to the inverse Fourier transform of this T JTC as a function of fx and y. And you know that this the amplitude transmittance of the filter is proportional to I. So we are plugging. So we need to take the inverse Fourier transform of that quantity, that is the intensity. So we have plugged in the proportionate value of this T, which is the intensity. So we have plugged in the value of intensity from equation number 29, from the last step of equation number 29 over here. And then you know that we have the inverse Fourier transform operator outside this curly bracket. So this Fourier transform will inverse operator will operate each of the term within the curly bracket, which we shown next. So you see that this inverse operator is operating on all these four terms. And then you know that we have taken the inverse Fourier transform of the first term, because the first term can be written as the convolution of two terms, that is O with convolved with O. So we have written that one over here, because you know that O will be multiplied by O mod square, that is capital O mod square is equal to capital O multiplied by the complex conjugate of capital O. And when you take the inverse Fourier transform of two quantities which are multiplying, you need to write a convolution sign over here as in equation number 31 step 1 shown in red. So O as at the image coordinates will be convolved with O star at the image coordinates at the image minus u and comma minus v. And you know that in the second step of the above of equation number 31 shown in the below, show in blue, and the Fourier operator will operate on the third term, that is it will operate on capital O, it will operate on O2 conjugate, and it will operate on the exponent term which is e to the power minus iota 4 pi fy and y naught. So these are the three terms. So three terms will appear in the when the inverse Fourier transform operator will operate, there will be convolution, two convolutions sign between the three terms. So you see that the exponent, the Fourier transform of the exponent will be represented by the delta function as given in the second step shown in blue in the last step of equation number 31. So similarly for the step number 3, which is written in black, the Fourier transform is the inverse Fourier transform is shown over here. Again, you know that the 3 terms and 2 convolution signs over there. Similarly, for the fourth term, we shall write the fourth term similar to the first term in red. So the green term in equation number 31 is shown. Okay, so you see that these are the 4 terms we have shown in the form of the convolutions between the first 2 terms. In the first term and the second term involves the convolution between 2 terms, and the second term and the third terms involve the convolution of 3 terms. The second and the third terms are the cross correlation terms. The second and the third terms are the cross correlation terms, because you can notice that O is being convolved with the O conjugate, that is O is being convolved with the O2 conjugate, and similarly in the third step O2 is being convolved with the O conjugate. So due to convolution between O and their conjugate counterparts, we can say that these are the cross correlation terms and are centered at the image plane at the coordinates this one, that is u is equal to 0 and v is equal to 2 y naught, and the second one is centered at u is equal to 0 and v is equal to minus 2 y naught, as obvious from the arguments of the delta functions respectively. Their integral representations are given below. So we are going to give the integral definitions of the third term and the fourth term. For the second term and the third term. So the integral representation for the second term is shown in equation number 32. So in the second step of equation number 32, we have carried out the convolution between O2 star and the delta function. That is the arguments of the u and v in O2 star will be replaced by the arguments of the delta function as shown in the second step. And then in the third step, we have given the integral definition of the convolution between O and O2 star, which is shown in the last step of equation number 32. Similarly, we are going to give the integral representation of term number 3 in equation number 31. So this is the integral representation of the term 3. And again, you know that here we are going to convolve O2 star with the delta functions as shown in the second step, and in the third step we have shown the integral representation of the convolution of O2 with O stars as given in the last step in equation number 33. The second and the third terms in equation 31, which are explained in equation number 32 and equation number 33 respectively, give the optical cross correlation between 2 signals O at the zeta and eta coordinates and O2 at the zeta and eta coordinates, and are mirror images of each other about the optical axis of the system. So you see that these are the mirror images of each other. To produce optical convolution between the 2 signals, that is O and O2, one of these signals, say for example O in the object plane given in the object plane shown in the figure given below the equation number 29, needs to be replaced by the mirror image, that is O as a function of zeta and eta will be replaced by O conjugate at the coordinates minus zeta and eta. Since O is a real quantity, so O conjugate will be represented by O, and O will be represented at the coordinates of minus zeta and eta. So O will be replaced by O as at the coordinates zeta and eta will be replaced by O at the coordinates minus zeta and eta, where this will be replaced over here in this setup, that is in this setup. So we are replacing O with its mirror image, so that we can obtain the equations in our desired form for equation number 31 and 32. Okay, so you see that once we carry out this mirror image transformation for the object O, such that the amplitude transmittance TA as at the zeta and eta plane is given in equation number 28 is now replaced by that given in equation number 34. So you see that we have represented the modified amplitude transmittance of the object because O will be replaced. O is now located at minus zeta comma minus eta plus y naught, and O2 is located at the same position as given in equation number 28. So you see that from this one, that is from the second argument of both O and O2, we can find that minus eta plus y naught is equal to 0 in equation number 34, and eta minus y naught is equal to 0 in equation number 28. So you see that from these two equations, from equation number 28 and from equation number 24, when we consider the second argument, you see that in both arguments y naught has the same value. It is obvious that the position of the signal in O does not undergo any change along the eta axis at the object plane. With this new transmittance function, the counterpart of equation number 32 and 33 will be replaced by the convolution between the signals O and O2. So you see that with this modification in the amplitude transmittance as given in equation number 34, now we can rewrite equation number 32 and 33. So after introducing the mirror image of O by O as a function of minus zeta and minus eta, and then rewriting the amplitude transmittance as given in equation number 34, and finding that the position of the signal in O does not undergo any change along the eta axis at the object plane. With this new transmittance function, the counterparts of equation number 32 and 33 will be replaced by the convolution between the signals O and O2. That is, in equation number 32, these O2 stars can be replaced by O2. And similarly, we can replace O in equation number 33 by O. The resulting optical convolution at the image plane will be mirror images of each other about the system optical axis. One will be centered at y is equal to 2, v is equal to 2y naught, and the other will be centered at v is equal to minus 2y naught. These two optical signals, cross correlations or convolutions, can be seen separated from the two terms, first and the fourth term in equation number 31. Contributing along the system optical axis provided their separations at the object plane 2y naught, satisfying the following inequality. So you see that we have four terms over here. The first term and the fourth term will propagate along the optical axis, whereas the second term and the third term will be directed along the center of the images. That is, the images will be centered at v is equal to 2y naught and v is equal to minus 2y naught. So these are the cross correlation or the convolution images. And you know that we want these images to be separated from the images going along the optical axis. So we want that the images corresponding to the second term and the third term should be separated, should be well separated from the term 1 and term 2, which are propagating along the optical axis. For the separation of that one, we are introducing y naught is equal to this condition must be satisfied. Y naught should be greater than half of the maximum value of W1, W2 plus 1 over 4 times the value of W1 plus W2. You know that W1 is actually the width of the signal O, and W2 is the width of the signal O2 at the image plane. And y naught, you know, that is the separation from the center of the optical axis along the vertical direction for one of the correlation signals, and minus y naught for the second correlation or the convolution signals. We have also defined W1 and W2 in one of the previous slides. In the previous slide, that is in the slide number 65, with the help of a diagram. So where W1 and W2 have been defined prior to equation number 26. So JTC based filters are superior to van der Rohe filters in the following aspect. Number 1, no alignment varies at the Fourier plane. You see that when we have the Waterloo filter, the main objective was that to replace the Waterloo filter at the same position where it was first exposed. So that condition is not that required for the this filter to be placed at the Fourier transform plane. The second is that this is useful for real time applications. And what are the inferior points? So this is inferior in comparison with the Waterloo filter in the following aspects. Number one, smaller sizes of input signals at the object plane. So, and number two, smaller use of system bandwidth. So you see that this is the main drawback, is that we have to use the smaller bandwidth because the sizes of the object O and O2 are smaller in comparison with the bandwidth provided by this lens L1. So these two objects are part of the segments, are part of the dimensions of this lens. So here we are not using the full dimensions of the optical systems. That is, the bandwidth is compromised. So you see that this is what we have, a compromised bandwidth in case of the this joint transform correlator.